Hello class, my name is Alejandro Ayala and I will be facilitating our collaborative work today on Raoult's law, Henry's law, and applying these laws to phase changes. Today's work will deviate somewhat from a traditional PowerPoint lecture, but as the lesson evolves, we will all get a better understanding of the material and learn about our roles in the learning process as well. To begin, I would like for everyone to get into groups of 3. There are 18 students in here, so there will be 6 teams total. Though it is not required, I encourage you to select students who you may not have previously known. Please arrange your desks so that you are sitting next to your group members and take out a piece of paper and pencil. On the board, I have written 4 concepts. I want each of you to write down on your paper in as many sentences as you want what each concept means. You may even define them or give a descriptive example of each. This assignment will not be graded, but after 5 minutes, you will be asked to present to each other what you wrote. Do not speak to each other until the 5 minutes are up. Ready? Begin. Okay. Now, I would like you to take turns reading to each other what you wrote. Let me know when you are done. What you have just completed is a rendition of what is called minute paper, and it is one of the many activities that can be implemented in the active learning teaching approach. The University of Minnesota 2022 describes active learning as a broad range of teaching strategies which engage students as active participants in their learning during class time with their instructor. The role of the instructor sort of changes into that of a facilitator. This approach utilizes group activities, individual learning, and reflection. The idea is that through interactive participation, you'll be working with the material in a hands-on approach, and hopefully gaining greater mastery of the material as it becomes more concrete and less abstract. I hope this activity allowed you to get more comfortable with each other and gets you warmed up for more group work. I hope the activity was not too intense and the anonymity allowed you to be more free in your thinking. As we progress together, so will our group work. And on this slide I have here a little visual of what sort of like the pyramid for active learning. Passive learning is obviously lecture, reading, doing things on your own, being told what to think about, things like that. Active learning, of course, is discussions, practice doing, and teaching others, sort of using the material in a hands-on approach. Okay, now Raoult's law. François-Marie Raoult was born in 1830 and was a French chemist and university professor who formulated a law on solutions that made it possible to determine the molecular weights of dissolved substances. He discovered that the freezing point of an aqueous solution is lowered in proportion to the amount of a non-electrolytic substance that is dissolved in the solution. A solution that conforms to Raoult's law is an ideal solution. Raoult's law is given by the expression Pj equals Xj Pj, where the P on the right side of the equation is the vapor pressure of the pure substance. This law states that the partial vapor pressure of a substance in a liquid mixture is proportional to its mole fraction in the mixture and its vapor pressure when pure. In general, the vapor above a mixture is also a mixture, so the total vapor pressure is the sum of the partial vapor pressures from each substance in the mixture. Okay, Raoult's law, an example. For this example, I will be taking an excerpt from De Novo 2017. Raoult's law states that the vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. We can look up vapor pressure of water at 25 degrees Celsius to be 0.0317 bar. The example states that 0.234 moles of sucrose acts as the solute and is dissolved in 5.56 moles of water. Dividing the moles of water by the total moles of the solution gives us the mole fraction of the water, which is the solvent. As you can see, the vapor pressure of water is equal to 0.0304 bar. This makes sense because water makes up 96% of the mixture, so the vapor pressure of water in a solution that is mostly water will be very close to the vapor pressure of pure water. Now, I sort of skipped a step here to make this example more easier. So the original equation gave us grams, and I just used the moles because what we're working here with is moles. So just to make it easier for this slide. Raoult's law, entropy, and chemical potential. Raoult's law has its molecular origin in the effect of a solute on the entropy of the solution. A pure solvent has lower entropy than does a mixture because at any given moment, you are less likely to know what molecule is present in any one point in the mixture because the other substance that is present might be occupying that space that you picked out. A mixture that has a higher entropy has less to gain from jumping into a higher energy state, such as that of a gas. So because of this, it is less likely to vaporize compared to a pure solvent. In other words, there is already more disorder in the mixture. Therefore, it has less potential stored energy that wants to be released. So now, how does chemical potential fit in with these concepts? So this is about chemical potential. Chemical potential is related to pressure. Raoult's law relates vapor pressure to composition. Therefore, through these premises, chemical potential is then relatable to chemical composition. The sort of if-then statements, if you lay them out, you can sort of get the very first statement and make a prediction about that very last statement. Raoult's law, ideal and real mixtures. An ideal solution is one in which the solution obeys Raoult's law at all compositions. This means the solute concentrations is close to zero or that the solvents and solutes are chemically similar. Raoult's law is not an indicator of the chemical composition where solute concentrations are higher. That is because the solute is surrounded by solvent and therefore has properties that are far from that of a pure solvent. It is found experimentally that in dilute solutions, where the solute is of high concentration, the vapor pressure of the solute is proportional to its mole fraction. Instead of the vapor pressure of the pure solvent, however, Henry's proportionality constant, K prime, is used in the equation to find the partial vapor pressure of the solute. So this very last point, we're jumping into something a little different now. Before we were using the vapor pressure of the pure solvent. Now we're going to be using a new term, the K prime, which is Henry's proportionality constant. Henry's law. William Henry was an English chemist. He was born in 1775. In 1803, he proposed Henry's law, which states that the amount of a gas absorbed by a liquid is in proportion to the pressure of the gas above the liquid. In dilute solutions, each solute molecule is surrounded by solvents, and the escape of the solute molecule as a gas is proportional to the concentration of the solute in the solution. This holds true for dilute solutions where the molecular species is the same in the solution as in the gas. In other words, Henry's law states that the vapor pressure of a volatile solute is proportional to its mole fraction in the solution. And here, where K prime is Henry's law constant. Now we're going to be talking a little bit about Henry's law constant. K prime. Henry's law constant is denoted as K prime. In the general equation, solubility of a gas, labeled C, is equal to Henry's law constant, K prime, times vapor pressure of the gas, P gas. K prime has units m over liters over atmosphere. K prime is linear and is equal to the tangent line of the curve at point x of b equals 0 in the experimental curve graph for that gas liquid K prime value. Okay, that's a little tricky, but that is when researchers plotted the mole fraction versus the pressure graph for a liquid gas combination, K prime ends up being the tangent line at the point where the mole fraction of the solute is 0. This implies Henry's law only works for low solute concentrations. In this slide here, I put the image of the graph and partial pressure versus mole fraction. K prime is equal to that linear line. And we were in the previous screen, we were given the equation for that linear line, which I'll go back real quick so you can see. Oh, well, anyways, I won't go back, but anyways, Henry's law, the linear line was the vapor pressure equals to K prime times the mole fraction of the solute. Okay, moving on. Henry's law, how is it different? Raoult's law looks into the chemical behavior of the solvents in a solution, whereas Henry's law looks into the behavior of the solute in the solution. So Raoult's law, solvent; Henry's law, solute. Raoult's law uses vapor pressure of a pure solvent, whereas Henry's law uses Henry's law constant. Henry's law constants are found experimentally and can be obtained from tables available in literature, such as chemistry books. Of course, we all use the internet for almost everything, so even the internet is where you would probably be getting those values. On this graph here, I showed the difference between Raoult's law and Henry's law, and as you can see, Henry's law, that's a much steeper line, and Raoult's law is less steep. So you would be assuming that the pressure for Henry's law, that the pressure goes up a lot higher with every slight mole fraction. All right. Henry's law description. Henry's law looks at how a gas is dissolved into a solution. If we know how much of a gas can be dissolved in a liquid, we can multiply that by the partial pressure of the gas of interest to get the actual concentration of the gas that is dissolved in the liquid. The example given by De Novo tells us that Henry's law can be used to analyze carbonation in drinks. A can of soda is carbonated with CO2. Henry's law could help us find out how much CO2 is actually absorbed by the liquid soda if we know K prime for water and CO2 gas, as well as the partial pressure of the CO2 gas above the liquid. The equation concentration of gas equals Kp of gas explains why CO2 fizzes to the top once the can of soda is opened. Upon opening the can of soda, the vapor pressure decreases because it is no longer contained in the small space in the can. Because we're dealing with equations, what you do on one side is what you do on the other side. So if on one side you decrease the pressure, the vapor pressure, that is by opening the can, on the other side you're also going to be decreasing the concentration of gas that is dissolved. This image sort of shows what I just explained. Active Learning 2. Now I will do another active learning activity, which is called case studies. I want you to get back in groups of 3, but this time get into groups with different people. As the title suggests, we will be coming up with case studies involving these two concepts that we have covered so far. There are 6 groups, so I want 3 groups to come up with a case study for Raoult's law and I want the other 3 groups to come up with a case study for Henry's law. You may create an imaginary scenario with imaginary variables, or you can use your electronic devices like tablets or cell phones to find examples of these concepts online to present to class. When one group is done presenting, I will ask the groups covering the other law if the law being used was appropriate or not. For example, in the case of the soda can, you would argue why Henry's law would be used for the gas component CO2 and not the solvent component sugary mixture. You have 30 minutes to complete this activity. Begin. Okay. Now, we covered 2 pretty complex topics. Now we're doing phase changes. Substances can exist in 3 phases: solid, liquid, and gas. Fusion is going from solid to liquid. Vaporization is going from liquid to gas. Sublimation is going from solid to gas without going through the liquid phase. Raoult's and Henry's law involve chemical composition and chemical behaviors. If a liquid is vaporizing into gas, this is indeed a phase change. If a gas is dissolved into a liquid, this again is a phase change. Using the soda analogy can give insight into these phase changes. It can be assumed that not all the CO2 bubbles out of the solution when you open the can of soda. Therefore, some of the CO2, is actually ingested as aqueous in the aqueous form as carbonic acid. Just a side note, carbonic acid is a weakly bonded molecule. So just sort of the general the general ideas I found in getting looking up information for this was that most of the CO2 gas, it comes out as burps. That's one source stated that. But anyways. Also, there's a limit as to how much of the CO2 will be dissolved due to the vapor pressure exerted when the soda is created. That is, by increasing the pressure, you can pack more CO2 gas in the solvent, which is the sugary liquid. Okay, learning activity 3. Now I want you to break into groups of 3 again. Select partners you haven't had before. You must create either a monologue, a speech, a play, or a dramatic reading of one of the concepts presented in class as a group. You are only creating one piece of work per group. The only rules for this activity is that your work must include and explain a component of the chemistry from this lesson. For example, you could create a monologue as if you were an atom of carbon that was trying to join a group of mercenary oxygens to infiltrate the territory of Cola Land. That's just an example I just made up. I want you to specifically state how Henry's Law or Raoult's Law would play a role. You have 30 minutes to create your piece. You could use any props, and the performance must be at least 5 minutes in length. Let me know when you are done. Comments and feedback. I would like you all to take out a piece of paper now and provide one comment about what we did today. I am especially curious about which activity you liked best, or if you didn't like any of the activities, tell me what would have been helpful. The point of active learning is to help you engage, so this is your chance to tell me what would help you do that in the classroom setting. I would also like a short note about my presence as the facilitator. Was I too instructive, or did I allow enough space for the class to work things out on their own? Research and resources. I would like to refer you to resources found online for this material. Besides your chemistry text, there are also great online video tutorials for everything we did, even the performing art portion. So as you can see on the screen on the left side, things like YouTube, Khan Academy, De Novo Tutors, writerscookbook.com. These are online resources that you can go to for the topic of the chemistry that we were covering today. I also listed, for those interested in active learning and how to apply this process, I also listed resources for you as well. The University of Minnesota reference in the reference section of this PowerPoint will also have great information in the process of active learning. In this website, you will find suggested texts, workshops, and different ways to become involved in the active learning community. If you visit the website, you will see that this is an evolving science. So people who come up with a great approach using active learning are encouraged to join workshops and to maybe even give speeches to promote their ideas that work. So that's actually great. That's how we improve education. Okay. I wanted to include a quick guide on implementing active learning specifically for this material, which I hope you carry with you to your next courses and use some of what you learned here either about the topic or about active learning approach. First, I will discuss active learning, and then I will discuss the substance of the lesson, the chemistry sub. In this case, it is chemistry. For active learning, if you plan to use it throughout the lesson and be consistent. I started with an activity and I ended with an activity. I prompted the students that there was more to come. Know the audience means apply instruction appropriate for age and grade. If you're teaching to college students, then make sure that you're using technical terms appropriate for them. By implementing an easy task at first, it helped the students become vocal with each other without having to feel vulnerable if they didn't understand the material. Gauge effectiveness means understand the audience and their level of willingness to participate. Perhaps the lecturer will have to add more icebreakers if the class is still a little hesitant at the beginning. Build on skills means implement activities that require more self-direction and contribution from the students to the class. Challenge students to be facilitators means not answering questions for them all the time, or it also means allowing them to explore possibilities with the risk of being wrong. That's how you do some of your best learning, when you're wrong. Emphasize what they did right, though, to keep that motivation level up. Evolve your approach means being open to feedback and building on what you did right and understanding what does not effectively get students engaged. We might think we have a great idea, it just doesn't translate well in the classroom. In terms of the chemistry being presented, Raoult's law and Henry's law was enough substance for one lesson. By limiting the material that is difficult, the students can better grasp and master it. Paraphrasing is a great way to get the key components across. By explaining what variables are important for each law allows the student to zero in on that point. Using a real-life example allows the student to apply the material and create a mental picture. Including phase changes in this lesson allowed the students to pair something abstract, which was the laws, with something more concrete, which is phase changes, which should be a little bit more simpler. Another example is the students are likely to better understand Henry's law if they have to logically work out how it fits with their case study. Provide support for the methods and procedures used works for two reasons. One, the students appreciate and have more confidence in what you are doing. Two, by knowing why the law was created, like the effect of solute on entropy, the student can associate it better to its key application, as in why Raoult's law came about. Checking for understanding allows you to know if the students understood the material and if your approach was effective. The final active learning activity would show if the students could apply what they learned and if they could successfully plan, execute, and deliver the project. The end. Thank you very much. Please let me know if you have any questions.